Do you know that decomposition reaction is saving our lives during car accidents? No? Then you are at right place. Let's understand how decomposition reaction can save our life or saving our lives. Welcome to Chemistry channel. My name is Mahantesh. See, we know nowadays in all the cars, airbags are mandatory, right? Airbags save our lives. But how do they work? Right? So you can see in this picture, this is the steering. Inside this, whatever is there will be a airbag. Inside this you can see some chemical is there. What is labeled here? Crash sensor. Means when there is a sudden change in the speed of the vehicle, this crash sensor will send an electrical signal, and here where the chemicals are there, the heating process will start. So once the heating process will start, the chemical will undergo decomposition reaction and produces gas. So because of that gas, what happens? The airbag will inflate and it will reduce the impact of accident on the human beings, whoever sitting in the car. So this is how decomposition reaction is saving our lives. This is the chemistry behind the airbags, how they are going to work. Then what are decomposition reactions? You can see here decomposition is nothing but one single substance is breaking into many, two or more simpler substances. Simpler, two or more simpler substances. You can see AB is a single substance. It's breaking down into A and B. Always what is important in decomposition reaction? There should be a single reactant. The reactant should be single. Products will be two or more. Okay, that is called as decomposition reaction. Okay, so decomposition can happen in many ways. It cannot happen on its own. It's like, I will give you one analogy to remember. It's a divorce between the couple. You know what is combination? Combination is a marriage between two people and forming one single family, right? A plus B gives AB, single product. Divorce means the single substance, the married couple are getting separated. So to get separated, to get the divorce, there should be some reason, right? Yes. Similarly, here there should be some force, there should be some energy which is acting on AB. Because of that, it is getting separated into A and B. So that energy can be in the form of heat. We can use the heat energy. Energy can be in the form of light, or energy can be in the form of electricity. See, even you want to break a chalk piece, you have to apply the mechanical force on this. Then only you can make it into two pieces, right? So to break the chemical compound, breaking of a chemical compound requires energy. If you are using heat energy to break a chemical compound, that particular process is called as thermal decomposition. Thermal decomposition reaction. If you are using light, photodecomposition reaction. If you're using electricity, electrolysis particularly, or electrical decomposition reaction. Here you can also call the light one as photolysis, heat one as thermolysis, right? Okay, so based on the type of energy, we can say different types of decomposition reactions. The first example given in your textbook is decomposition of ferrous sulphate, FeSO4. But actually I will little zoom it. Let's check the color here. This is ferrous sulphate, but it is not simply ferrous sulphate, it is ferrous sulphate heptahydrate. We call it as green vitriol. Means there is a water of crystallization. Therefore, what is the color of this? You can see light green. Light green. Initially, when you heat it, this symbol represents heating. When you heat it, first what happens? Ferrous sulphate will form and water of crystallization will escape as water vapor. Then if you keep on continuing, here in the second picture you can see, here if you carefully observe, there is a droplets of water. Where it came from? Because of water of crystallization getting evaporated. Slowly the color will change from light green to it will become reddish brown. So what is happening here? Okay, I will okay, this much I will erase. I will write it here, removal of water. So here ferrous sulfate will decompose into ferric oxide plus two colorless gases, SO2 and SO3 will form. You can't see them, they are colorless gases, but they will also escape. We have different tests to confirm them. Okay. So overall reaction is ferrous sulfate decomposed into ferric oxide, sulfur dioxide, right? This is solid, this is also solid, this is gas, this is also gas, right? So try to balance this part you leave, try to balance this. Fe2 are there, so put 2 here, sulfur 2, so 1 1 2, 8 oxygen, 3 plus 3 plus 2, 8 oxygen, right? Okay, so what type of decomposition reaction is this? See, there is a single reactant breaking down into three simple substances. Therefore, this is a decomposition. It is happening because of the heat. So this is an example of what? Thermal decomposition reaction. We can call it as thermolysis of ferrous sulfate. Okay, let's go to next. Thermal decomposition reaction, some more examples. Very nice experiment is there. See, here there is a test tube and we have taken a material here which is initially green in color, light green you can see, and we are heating it. Then there is a test tube, delivery tube coming into the another test tube. Another test tube contains some clear solution initially which is changing its color, right? So what is this? This green color substance is copper carbonate. Copper carbonate. So when you heat it, it will decompose into copper oxide and becomes black. Copper oxide is black. And carbon dioxide gas is formed. Carbon dioxide will pass through this delivery tube into this. What is this solution? Lime water. So lime water is changing slowly. It changes to milky. So lime water turns milky, confirms the presence of CO2 gas. So can you write the equation here? CuCO3 on heating forms CuO plus CO2 gas, right? So this is solid, this is solid, this is gas. I have already shown with arrow mark. This is green in color, this is black in color. Carbon dioxide is colorless, but it is turns lime water milky. We have seen this experiment in the previous combination reactions. You can check that as well. Okay. Similarly, if you take calcium carbonate is white in color. It will also decompose to form calcium oxide, which is same white in color, plus carbon dioxide, which turns lime water milky. So because there is white and white remaining, visible changes will not be there, but you can check the CO2 gas emitted. So these two are also examples of thermal decomposition reaction. Next, very important example, lead to nitrate, PbNO3 twice, on heating decomposes and forms three products. We'll see what are the three products. Lead nitrate you take, PbNO3 2. So the color of lead nitrate is white. So we'll write here white. It is a solid. Okay. On heating, it is decomposing and forming respective metal oxide, that is lead oxide, which is solid, and the color of lead oxide, if you observe slowly, it's changing to from white to yellow. So it will be yellow in color. Plus there is some brown gas is released on heating. So this is a NO2 gas. NO2 gas is what? Reddish brown gas. Reddish brown gas. And you can see in the third picture what is happening here. Fourth picture, there is a glowing wooden splinter, you can call it a splinter or wooden stick, whatever. It's glowing, it's not burning. When you're putting it into this container, it started burning with flames. So only one gas can do this, that is oxygen. So oxygen, what it do, it rekindles glowing wooden splinter. So that is the confirmation for oxygen gas, right? So there are two gases released. This is colorless gas. So one is reddish brown NO2 gas, nitrogen dioxide. Another one is colorless oxygen gas, which you test by this way. Lead nitrate is decomposing into lead oxide. So white to yellow, yellow. Both are gases, so this is only a solid formed here. So that is the observation you can write. Now pause the video and try to balance this. Okay. So 2, 2, 4, 1. 2, 2, 4, 1. You can check, it will be balanced. Same reaction can happen with other nitrates, like you take zinc nitrate PbNO3 twice. On heating, it will form zinc oxide plus NO2 plus O2. Balancing will be same, 2, 2, 4, 1. You can remember this one. Okay, and then what you can take, lead nitrate, zinc nitrate, calcium nitrate you can take. On heating, it will form calcium oxide, nitrogen dioxide, okay, oxygen. So 2, 2, 4, 1, same. Instead of calcium, you get a copper, but if you take potassium nitrate, KNO3, it will not form these three. It will form only respective nitrite and oxygen gas. Okay, that is the difference. Remember, this is the difference here. Okay. So if I write 2 here, if I write 2 here, 2 into 3 6, 24 plus 2 6, right? So this will be balanced. Sodium nitrate also forms same way. Sodium and potassium, they don't form respective oxides, they will form respective nitrites. This is nitrite, potassium nitrite. This is what? Nitrate. Okay, no NO2 gas formed. These are all examples of thermal decomposition. One more very interesting example is there. What is this orange colored substance? Orange colored substance is ammonium dichromate, Cr2O7, NH4 twice Cr2O7. This is called as ammonium dichromate. Dichromate compounds are usually orange in color. What's happening here? We call this particular reaction as chemical volcano. Chemical volcano. Nice experiment it is. So when you heat ammonium dichromate, little bit spark you put, it will continue burning automatically in forms like this. It looks like black, but it is actually, or it changes to green residue. Okay, what is this green residue? Chromic oxide, Cr2O3. And there will be a gas also released. What are the gases? Nitrogen and water vapor. Water in the form of gas. Okay, why we call it as chemical volcano? Because it burns like this. Check. See, this is actually how it looks when you observe it carefully. You are what observing here? Flashes of light. So it looks like volcano, right? So flashes of light and all. So write the equation for this. Ammonium dichromate on heating will form chromium oxide or chromic oxide plus N2 plus H2O. Okay, so this is the decomposition reaction. Okay, so try to balance this equation on your own. I will write the observation here. This is orange in color, this will be green in color. So what you can write here, green residue is formed, and nitrogen is colorless, water is colorless, so there is nothing observation for gases. You can write only for ammonium dichromate, orange to green. Okay, have you balanced this? Very simple. Check nitrogen 2, 2, hydrogen how many? 4 into 2, 8, but here only 2, so make it 4, 4 into 2, 8. Oxygen 7, chromium 2, oxygen 7 means 3 plus 4, 7. So this is balanced. Balancing is very easy. Okay, so this is also example of thermal decomposition reaction. In thermal decomposition, one more type is there. We call it as thermal dissociation. What is this thermal dissociation? Check this example. Initially, you have taken copper sulphate pentahydrate. Copper sulphate pentahydrate. This commonly called as blue vitriol because you can see the color blue color. So on heating, it is changing to white. White because it's losing its water of crystallization and forming copper sulphate plus 5H2O. This is what thermal decomposition. But if you cool this copper sulphate and leave it for some time, you are changing the condition. Initially heating, after cooling, if you cool this, what happens? It will absorb the moisture from the atmosphere and turns back into blue color. So these kind of reactions which are reversible, okay, a reversible thermal decomposition reactions, specifically reversible thermal decomposition reactions, are called thermal dissociation reactions. Thermal dissociation reactions. Okay, a reversible decomposition reaction brought about only by heat is called thermal dissociation. One more example I will give you one more example here. Ammonium chloride. Ammonium chloride you take. When you heat, reversibly you have to write the symbol like this. When you heat, it will form ammonia plus HCl. Ammonia and HCl, if they come in contact with each other and you cool them together, you will get ammonium chloride back. So this is an example of thermal dissociation. Okay. One more, nitrogen tetroxide, N2O4. On heating, it will form nitrogen dioxide, two molecules. So nitrogen dioxide, if you cool, you will get nitrogen tetroxide back. Okay, so these are all the three are examples of thermal dissociation. Okay, reversible reaction symbol is this. Don't do the mistake. Okay, right. Next comes very important one. Apart from thermal, what we know? We know electrolysis of water using electrical energy. Electrolysis of water is a very famous experiment. So I have a simulation for this. First we'll see that and come back here what is happening. So here, see, this is a simulation. You can see the setup here. There is a glass beaker. There is a battery source around 12 volt. There is a rheostat to confirm, increase or decrease the resistance. Anyway, this we can perform this experiment at home also. The rheostat is not required. And whichever is connected to positive terminal of the battery, that is known as what? Anode. Sorry. Negative terminal of the battery, whichever is connected, that is known as cathode. So when I pass the electricity here, when I switch on, see, you can observe the gases have started collecting. Initially these test tubes contain water. So water is going down because the gas is formed at respective electrodes here. And if you observe here, the gas is less. Here the gas is twice whatever collected here. Okay, wherever you're collecting, the more gas is there, that will be cathode. Less gas wherever it is collected, anode. Cathode is the one which is connected to negative terminal, so that is black wire. Anode is the one which is connected to positive terminal, that is the red wire. Okay. So what is happening here? Let's check. So in the electrolysis of water, what was happening? Two reactions are happening. Two reactions are happening. Very important, you should know there were two electrodes we are using in electrolysis. We will learn about these things, and these are submerged into water, and it is connected to positive, or one is connected to positive terminal of the battery, another one is connected to negative terminal of the battery. Positive terminal connected one, we call it as what? We call it as anode. Anode means add means positive. The negative one connected is known as cathode. The electrodes, we call these as electrodes. Electrodes are the metal strips or even the pencil what you have at home, that can also act as electrode, graphite. Okay, so what we observed, two test tubes kept in inverted position. In one we collected this much of gas, in another one double of that gas. So this will be your oxygen gas, this will be your hydrogen gas. So electrolysis of water means what? You are splitting water. Water is breaking down by electricity or electrical energy into respective elements, hydrogen and oxygen. Okay, if you balance this, you will get 2H2O, it will give you 2H2 plus O2. Therefore, you can see here the respective, here 1 it will be. Okay, the respective ratio between hydrogen and oxygen gas is 2:1. Okay, so hydrogen is cation, so it will form at the cathode. Cation will move towards the cathode because positive will attract towards the negative. So hydrogen will form here, oxygen will form at the anode. But that and all is not necessary as of now. We'll learn it when electrolysis we learn. Here what you should know, that the ratio between the volume of hydrogen is to oxygen gas is 2:1 because of this. Okay, next one more simulation, that is photodecomposition of silver bromide. Photo means you are using the light energy here, right? You know, photosynthesis, light energy used by the plants. Okay, so you're bringing about, or you're breaking a compound by using what? Light. Okay, let's see the simulation. Okay, you can see here, this is the light source, this is the compound silver bromide. You can also take silver chloride, no problem. So once you start the light energy, when you put the light energy on this, over a period of time, it will slowly change its color. So it will become silvery gray color substance. Initially it was white in color, slowly it will turn to silvery gray color substance. Why? Because of what? Sunlight. Sorry, because of light, it is getting decomposed. It is getting decomposed. Okay, see here what happened here. You taken silver bromide, which is white in color. So on, when you put the light on the silver bromide compound, it is getting decomposed into silver, and bromine gas will be released. Okay, so here if you balance this 2 and 2, same reaction happens with silver chloride. It will also undergo photolytic decomposition reaction and form silver and chlorine gas. So here again you can write 2 2. Silver compounds are photosensitive, therefore we store them in colored bottles. Colored bottles. There may be a question, why silver chloride, silver bromide, silver nitrate solutions are stored in colored bottles? Because they undergo decomposition reaction in sunlight or in on the presence of light. So if we keep them in colored bottles will prevent the light to enter the or to reach the chemical, so we can save it for longer time. Okay, so this is the photodecomposition of silver bromide. So these are all examples of decomposition reactions. Next class we will learn about displacement reactions. Okay, until then, take care. Bye bye.